Sorry, Mari. Uh, Maria, should we start?
Yes,
So we are
you can
ending.
wait if you want for 10, 15 seconds, but
I
we
would
are
wait
ready.
for it. I would wait for a 1 minute.
All right.
Okay, so thank you everyone joining the room, and let's wait 1 minute to start. I see people joining. We have 15 participants. Welcome everyone. I cannot see if the attendees, if you have any doubt or you want to say something, please use the chat because otherwise we cannot see what you say. But if there's some issue, you don't see the slides, if you detect something, please everyone just write in the chat, and Maria or Mel or me will react accordingly.
The other option you have participants is to raise your hand, maybe at the end of the presentation.
Okay, 1 minute has passed, so let's start. Welcome everyone to the 10-week webinar series of the Presence Project. It's a pleasure for me to introduce the project itself and do the intro before Mel's talk. So today, let's say we'll have two presentations. I'll give a general overview of what is Presence about, what the Presence project about, and then Mel will give a short presentation on the feeling of presence, what it is, what compose presence, how we measure it, and what we are doing in this project to do. So in this project we are building a tool set for hyper-realistic and XR-based human-machine interaction. And you will see what this means. When we conceptualized this project, we were obsessed by the idea of how humans are represented in the so-called metaverse, virtual worlds. In the end, how you as a human are represented in these virtual worlds, how machines are represented in these virtual worlds, um, and which technologies we need to use and we need to improve in order to increase this feeling of presence. In the literature, you can find different definitions of what's presence, which are the basic ingredients that conform the feeling of presence. Is not only one thing; there are many things that impact the feeling of presence. We'll get into details later, but in the end, the objective for us is to get one or two steps closer to the already old dream of XR enthusiasts of be anywhere, doing anything together with others from any place in hyper realistic environments, and reduce this presence gap, right? So when you think in virtual worlds and you check the social VR applications that we see out there, this is what you get. Of course, there are some more advanced uh, deployments as the ones we are developing in this project. But in general terms, what you see in the screen is what you get for a let's say a virtual collaborative meeting. So a bunch of people around a virtual table represented with cartoonish avatars that more or less behave as the user behind this avatar. And this presents different limitations. We focus here in three of these limitations. First, the human presence, the human representation, how you are represented in this world, and how we can represent ourselves with photorealistic quality in these environments. The second limitation is the touch. Normally, you cannot touch things in virtual worlds. In this project, we're improving different haptic devices and generating interfaces in a way that different haptic devices from different manufacturers can interact between them, because let's say, these are relevant issue in the market today. And finally, the human behavior and how smart avatars look like and behave representing us or representing some intelligence that drives them, right? This is what we call intelligent virtual humans. So we have three technical pillars: holoportation, haptics, and virtual humans. In the holoportation, what we are trying is to build hyper-realistic holograms to connect remotely people. I'll get into details later. In the haptics, as I said, we are generating 3 new haptic devices, improving 3 haptic devices, and building the transcoding middleware so different manufacturers can build these devices in a way that they get to the market in a way that they already can talk to each other, so we are not close in one haptic provider. And then the virtual human representation, which technology we can use to represent ourselves without having holoportation, meaning cameras around us, or without having haptics. How we know that the body moves, how we recreate natural movements, how we connect these avatars with LLMs, and in general terms, how we make these avatars being smart or intelligent, behave as realistically as possible. So I just want to show you some pictures, GIFs, to give you a status update of what's the current status of the project. Here you can see, for instance, a pass-through holoportation. One of these 2 users is not there, right? Of course, you can see clearly which is the user that is not there, but you can start to appreciate the photorealism of it. That was the status more or less in year 1 of the project. Now we're in year 2 of the project, and this is improving slowly. You don't see my back, but this is volumetric capture cabin with many cameras, and by the end of the project, we expect to deliver full body reconstruction in really high quality. The problem, as I said, is that you start with something like what you see on the left of the slide, on cartoonish avatars that really do not represent well the how to say, the feeling of the user. They don't represent the users in a realistic manner. And we are getting in this project to something closer to this. As you can see, there's a huge difference, especially when you want to transmit something relevant. Well, when you want to transmit feelings, you need to be real at some point. Holoportation is not an easy task. You need to do capture, you need to do reconstruction, you need to do compression. Here, for instance, you can see how the compression method that we are developing in this project is working. Again, that was year 1 of the project. This is improving. I won't show you the numbers here. If there is real interest on see how this performs on over the top devices, just drop us a line. And we are also working on scalability, right? Once you are able to capture one user in a volumetric manner, in a volumetric format, you want to transmit this data, and when you have 2 users, you want to have more users, right? In order to achieve that first slide that I show you, where you had like 12 or 20 users around, when you want to represent all of them with volumetric video, you achieve you hit some bottlenecks that you need to address. And this is also something that we will discuss, I think, that in 3 weeks from now. I won't get in more details, otherwise I will consume Mel's time. In haptics, this is what we are developing in this project: 3 different haptic devices: a vest, a cushion, and gloves. And you can see here, for example, how they are already interacting. Right? Press. For instance, if you are in a VR game and you have a sword, and you want to touch, let's say, a stick, not a sword. You want to harm anyone. You want to touch with a stick someone. That's the feeling that is going to generate. You are going to feel in your back that the sword is getting through. Right. In this video, for instance, you can see highs from SenseGlove or Wear Package 3 leads, where two of these devices are haptic devices are interacting between them. The gloves from SenseGloves and the cushion from the former partner Actronica. Here, what Heise is doing is touching himself with the gloves, so not touching himself, but he's feeling this touch in his chest. Imagine you can use this to tap in the shoulder someone, to give a hug and feel this pressure, right? So that steers feelings of co-presence, of being together, touching each other in the real world is very relevant. In the virtual world can be also very relevant, certainly in different scenarios. And then the virtual humans. This is not working. In virtual humans, as I was saying in the beginning, we are trying to make virtual humans to look more natural. What you see here is seven virtual humans with different walking styles that behave to the physics that you deploy in a certain 3D scenario. At some point, you can see that some of them fall, but as you can see, they react to the obstacles and they behave accordingly. Here, for instance, what you see is a fully virtual avatar. This is the user view. This is an intelligent virtual avatar, completely automatic. In this video, basically the user says hi, and the virtual avatar understands that you are saying hi, and behaves consequently. No? Approach, gets closer to you, and waits at a social accepted distance. Or here, for instance, this is smart, what we call a smart avatar. There is a user behind the avatar representing a real person, right? So just with your glasses, this avatar will behave exactly like your movements, the movement of your face, with your voice and so on. These are the three technological pillars, right? Three very different technological pillars that we are deploying in different use cases scenarios. A professional collaboration scenario. There is a virtual meeting around the table where different users with different user representation types and different, let's say, capture and rendering capabilities interact. Here we have Tom that is at home. He will wear only a glass, a VR headset, and haptic gloves. And you have Emma, that she's in the design studio, but she only has the headset. And then you have the avatar specialist, also only with the headset. And then the industrial engineer, that is Lisa, is completely holoported. So all of them, they can see each other, and each one is represented in a different way. A manufacturing training scenario, especially for complex, unsecure scenarios that you want to replicate, or for landing of new employees. More or less that in the previous scenario. In this case, we had an intelligent virtual agent, right? You don't want to, let's say, of course, you want to have your supervisor there with the highest quality, holoported, and you want every new employee to see how an holoported user manipulate a specific machine with high realism. But there are certain parts that you don't need an employee to explain. An intelligent virtual avatar, a realistic intelligent virtual avatar can do that job for you, reducing, of course, time, effort, costs. In the health domain, for instance, in VR is already used, for instance, for reduced anxiety in surgery procedures, or when needles are involved, right? So in this case, we have an intelligent virtual agent that explains you how the procedure is going to be, but also you can have physical and visual contact, audiovisual contact with a family member or a friend, right? You're sitting there, you're about to get a surgery, but you can hold the hand of a family member. This is useful in many environments. And lately we have through the talks that we had with different use case partners, we see that this is very useful in isolation, in undesired isolation situations, right? To be able to see each other and have the feeling of being together, which all these technologies will play a very relevant role. Similarly, a cultural heritage use case, different visitors just with glasses want to experience together a cultural heritage experience. It's full of avatars that introduce you specific work arts. And in this case, we have a time witness, a person that has been recorded full volume and that explains you certain parts of the environment. Imagine a museum. You want to give importance to the people working in the museum, to the curators, to the experts, but they are not available all the time. They are doing their thing, they are researching and so on. So this is also a way to put in value the humans behind the work in the cultural heritage use case sector for sure, but in many others. That's everything from my side. I think I was more or less on time. So now I leave the floor to Mel's presentation about the feeling of presence. Thank you very much.
Thank you, Sergi. I will now put up my slides. And since the project is about presence, it's called presence, we have to have an understanding of what presence is and how to measure it. So this is my view of presence. I'm going to talk for roughly half an hour, and then there'll be time to questions for both Sergi and myself. So I'm going to talk about the illusions of virtual reality. I'll give a couple of examples: fear of heights and police racism in the US, then the measurement problem, and if the last one on sentiment analysis, I'll only do if there's time. So for me, the key illusions are these: the feeling of presence. We start from sensory motor contingencies. Look at this person, he's in virtual reality and he's perceiving the world much as he does in reality. He's looking around, you didn't see that, but he's reaching, he's touching things and so on. These are called sensory motor contingencies. They're how we use our body to perceive. And to the extent that virtual reality supports this, to the extent that virtual reality supports natural sensory motor contingencies, so the hypothesis is that you get this illusion, which I call place illusion, which is the illusion I am there. Now let's take a second example. Let's just say that the person responds personal, they meet expectations. Have a look at this video. I guess you can guess what they're doing. They're playing table tennis in virtual reality. So to the extent that the game and their behavior and their expectations and the physics meets their expectations, they have this second illusion, which is plausibility illusion. These events are really happening. Let's go on to the third one. We've got first person perspective plus multisensory integration. You have a virtual body and you look down and you see that virtual body from first person perspective. You move and it moves with you. So the first person perspective 1pp plus the multisensory integration, which in this case is visual motor synchrony, you move and the body moves with you, gives rise to this feeling of body ownership. This feels like my body. And place illusion, plausibility, and body ownership give rise to the last one, which is these people happen to be physically together, but they may be separated by thousands of kilometers, and it's co-presence. They're here with others, and actually they're all attending a virtual rock concert together, and they can see each other in that rock concert. So have a look at this video. Sorry, let's press the wrong button. Again, go back.
Flying high isn't fun for everyone, though.
Hello, world.
Acrophobia, or fear of heights, is one of the most common phobias, but this virtual reality therapy hopes to help.
Sweating again.
Said sweating
Shan
again.
here can confidently fly a plane, but when it comes to heights in general, it's a different story.
Oh, no.
He's got tasks to like
I've got to move.
pull a lever to pull that cat back from out over the precipice.
I can't move while I'm out there.
He can't move while he's out there.
I couldn't go up a ladder.
So the question is, how is it possible that people become anxious in this virtual scene? I mean, he's just looking at some pixels in reality in the display. So how does he become anxious? So for this to happen, they must have these illusions. First of all, they're in a different place. Sensory motor contingencies. He looks around the world. He sees updates in his visual system, much as it would in reality. This gives rise to place illusion. Second, these events are really happening. He's pulling back on that lever. The device comes back or moves forward, depending. Events are really happening. This is plausibility. So in spite of knowing that these are illusions, it still generates realistic behavior. For someone who has fear of heights, he has the fear of heights in virtual reality, because overall, the safe computation for the brain to make is that this is really happening, because it might be. So place illusion, I have a strong view of place illusion, this aspect of presence. It's the illusion that you're in the virtual space in spite of the fact that you know you're not there. It's not to be confused with many different interpretations of presence, like attention, interest, flow, task performance, etc. These are all important, but they're not presence, they're not place illusion. So pi in this definition is not applicable to our normal everyday sense experiences, because it's part of it is, you know, it's not true, but nevertheless you have this feeling. So the fact that it has occurred, that it actually occurs, is witnessed by the surprise that people have often when they enter a VR. Look at these examples. These are just from games.
Okay, they getting straight to it, I see.
So he's looking around some scene.
Oh!
And suddenly,
No.
it's very powerful. Here's another one, going back to the heights one. He's going up in an escalator. So nothing really is happening, but you can see their responses. And this is not atypical, it's not a joke. So the fact that presence occurs is witnessed by the fact that the surprise that people exhibit when they enter a VR and something unusual happens. And it's surprise in the everyday meaning of this word. It's a perceptual shock, but also it's surprise in the technical meaning as entropy. And the need to minimize surprise is to be able to function in the new environment. If you don't get over the surprise, you can't function at all. And that's both surprise in the everyday meaning of the word and in the technical sense of minimizing entropy. So let's go on to plausibility. I've been talking about place illusion. We did an experiment. It's a complicated issue, this plausibility, much more complicated, I think, than place illusion. We did an experiment some time ago, 10 years, well, an experiment with medical doctors that illustrated a failure of plausibility. The doctors interact with patients, and those patients in the virtual reality unreasonably demand antibiotics. These are real doctors. They become stressed in dealing with these virtual patients because they're demanding antibiotics and it's just not appropriate. So the more experienced doctors were less inclined to prescribe antibiotics to these virtual patients. The younger doctors did so eventually, but there was one failure of plausibility. They had a computer on their virtual desk, but it couldn't be used because at that time, 10 years ago, the resolution wasn't high enough to display text in a reasonable size. So plausibility is these doctors got very nervous and very took it as real, but there was this one aspect that kind of threw them out the environment a bit, that there was a failure of expectation. They couldn't use the computer on the desk. Here's another example. So, by the way, plausibility doesn't mean realistic. Here's another example. This is from that same fear of heights study I showed you before. And at the end, when participants, after several weeks of training, they got up to the very top floor, there was a whale swimming in the atrium. And nobody said, "Oh, this is ridiculous. What's a whale doing there?" They just accepted it. So this plausibility is quite complex. And I think it's really, if you're into the research and you're looking for a research topic, plausibility is a really interesting topic to look into. And here's the body ownership. Again, I start that again. So here the person sees their body from first person perspective. She sees it when she looks down. She sees it in the mirror, and as she moves, the body moves with her. So we have first person perspective, visual motor synchrony, and this gives the impression, the illusion that this is your body, even though you know it's not. Why? Because in your whole life, whenever you've looked down towards yourself and you've seen a body, is your body. So again, the simplest hypothesis for the brain to entertain is that this is actually your body. So I'm going to give an example of how we've used all this in a practical application. It's a paradigm I called GREP. It's the golden rule. It's called the golden rule embodiment paradigm, and it's to help people overcome, let's say, bad behavior. In the example I'm going to be showing, it's police racism in the United States. So in general, the paradigm is that you're involved in an action that causes harm to another, the victim. You're not maybe directly involved, but maybe you're a bystander. You let it happen, you don't intervene. You then experience the scenario again from the standpoint of the victim. And then sometime later, there's another test, like a week later, you're involved in another similar scenario that also causes harm to another. The question is, how do you respond, having experienced it as the victim? Now, in experimental settings, there's normally a control group who experience the whole scenario, but never from the embodied perspective of the victim. So we did this. We actually went to the US. This was organized by Google. We went to an inner city police department in the United States. There were 37 patrol officers we worked with. They interrogated a male black robbery suspect, and their partner, virtual partner, was violently aggressive and racially abusive towards the suspect. So here's your partner, here's yourself here in the mirror. You can see your virtual body. Here is your partner who's being abusive. This is from the point of view of the victim. This is the control condition where you're just watching everything from the outside. Here's a reflection of yourself in the mirror, in the window. And 3 weeks later, they came back and they're in a virtual cafe talking with this same abusive officer, and a black man enters the cafe, and immediately that abusive officer started harassing him, accusing him of wanting to steal some woman's handbag. The question was, how did you respond? Did you let it go through? Did you just say nothing, or did you intervene? And this depended on whether you'd experienced it as the victim or you're in the control group. So this is that second scenario in the cafe, the customer standing by the counter. There's the abusive officer. The customer says he's done nothing, and I'll show you a video now. So let's wind this forward a bit. There's by the way, we filmed this during the pandemic. and the only person available to play the role of the police officer was the wife of one of the experimenters. So it starts off in the morning. You're in
Good morning,
your
guys. My name is
you're in your
Jennifer, and I'm here
bedroom,
to share
and you
something
just
really special with you.
do some
I'm going to show you
exercises
a
to
set
get
of
this
4
feeling of
simple
embodiment.
exercises that you can do very easily.
Won't dwell on this, and then you move to the police department, and now you're embodied as that same character, but now in the uniform. Again, you see yourself in the mirror. The sergeant comes in and explains the situation.
Good morning, officers. I have an update about the jewelry store burglary this morning. We managed to pick up 2 subjects, and we have some leads. We caught this guy 1 block west of the... So what do you say? I'll go handle the first subject, and both of you go interview the second one?
Okay, so now the interrogation.
Here. So, you want to get started?
Sure. Tell me your name.
Look, man, let me go. I haven't done anything.
Listen, we can do this the easy way or the hard way. And trust me, you do not want to test my patience. So either you start talking right now, or we're going to be in here for a long time. Oh, no. Look at that. The equipment isn't working. Oh, no. I'm talking about rights. Remember that paper you signed? That gives me and my friend here the right to do whatever the we want. So you listen carefully now, My friend here is going to ask you a question. Just answer it. That's 3 strikes right there, So you stop whining about a lawyer, you understand? I'm giving you one last chance to start talking.
Oh, you gotta believe me, man. I had nothing to do with this. I was just trying to catch the bus. Let me go, please.
Man, this guy. You know what? I don't have time for this.
Okay, so then in the victim group, we start it off where you're the victim, but you're in the cell before the whole interrogation started. And this again is an embodiment phase.
Lift your right
He
foot.
makes you move, you move your
Put it back
body,
down.
look down at yourself and so on. Let's skip this. And then you're in the interview room. We don't really handcuff the people. We just tie the 2 controllers they're holding together. And then they're in the interview.
So,
and now they
you want to
experience
get
it from
started?
the point of view of the victim.
Sure. Tell me your name.
Look, man, let me go. I haven't done anything.
Oh, no. Look at that. The equipment isn't working. Oh, no.
Oh, you gotta believe me, man. I had nothing to do with this. I was just trying to catch the bus. Let me go, please.
Man, this guy. You know what? I don't have time for this.
Okay, so then this is the control condition.
From here.
And as I said, in the control condition, they're never embodied
you
as
wanna
the
get started?
victim. They only see everything from the outside. And then finally, they come back. They says here 1 week later, but it actually was 3 weeks later. This is the cafe scene.
Hi, how you doing?
Hey, I'm fine. How are you?
Great. Been so busy, man. On my day off last week, went to see the game. You follow? Damn it. Look at that. Hey, you. What the hell are you doing? I'm talking to you. What the hell do you think you're doing?
Me? Look, I'm just here for my coffee, man. I don't want any trouble. Relax.
Don't you tell me to relax. I saw you staring at that lady's bag.
Come on, I wasn't staring at anything.
Are you saying I'm lying then? Are you accusing me of lying?
Nah, man. I don't know what to say. I'm just here for my coffee, and then I'll leave.
Guy coming in here like he can afford a coffee from this place. Step away from that lady.
But I haven't done anything wrong.
Walks in here dressed like that.
This is crazy. Are you seeing this?
Let me go.
Shut the up and do as I
did
say.
nothing wrong. What's your problem?
Freeze on the ground now.
Okay, so that was obviously acted. This is a
Hi,
real
how you doing?
subject. This is a real subject.
Not bad.
Here.
How are you?
Great. Been so busy, man. On my day
I'll
off
wind it
last
forward
week.
to the critical part. So they have the conversation. And now watch what happens. This
Damn
is
it.
a real subject.
Look at that. Hey, you. The hell are you doing? I'm talking to you. What the hell do you think you're doing?
Me?
Yeah, you. Who else?
What? I didn't do anything. What are you talking
officer,
about?
what are you talking about?
Can I help you with something?
So
I
he
saw what you were
starts
trying to do.
to
Don't act innocent.
Look,
starts to
I'm just here for
intervene.
my coffee, man.
Hey, officer,
I
I
don't
was
want
standing
any
right next to
trouble.
him the whole time.
Food
I need you to
and
step to the
meat.
side.
What's
Back
your
up.
problem?
Officer.
Freeze!
Whoa,
On the
whoa,
ground,
whoa.
now!
Put your gun.
So what happens is that two independent coders observed the scene. They didn't know which condition the participants belonged to or the purpose of the experiment. And there were 29 events that the coders were asked to rate. Like you saw one of them when the victim looks at you and says, "Are you seeing this?" The coders rated each act of the participant as in support of the officer or in support of the victim. And the probability that helping behavior was more than 80% in the observer condition was about 20%, and in the victim condition was about 80%. So this intervention, even though everything was virtual, actually seemed to change the behavior of the officers, at least in virtual reality. Now, in virtual reality, obviously, there's the issue of how to measure presence. The illusions, place illusion, plausibility, body ownership, gives rise to subjective feelings or qualia. How can we measure these or other associated feelings? We're going to consider the surprising connection between place illusion and eye scan path entropy and a method based on color measurement theory. So avoid sole reliance on questionnaires. There are questionnaires are okay, but not as the only instrument you use for various reasons. One is they're actually difficult to analyze correctly. The statistical test assumptions usually are not meant. You can use physiological measures, but you need specific circumstances to get a physiological response to a threat, and that's not always appropriate for the application. So the first thing we looked at was minimization of surprise entropy. This is again quite old, but we brought it up to date recently. Participants were in an environment that was gradually forming, so triangles were just appearing at random all over the place. And when finally the participants realized where they were standing on a high column. That's the stress-inducing condition. Or everything was the same, but they realized they're standing on the ground. And there was another random condition where all the polygons were the same, but that's just rotated randomly. So the participants never made sense of what these were. And we measured head gaze direction, entropy, and skin conductance responses. So entropy, remember, is a measure of randomness. It's not a measure of variance. It's a measure of randomness or disorder in the environment, in any system. It's a way to quantify how much uncertainty or chaos there is in the system. Its formula is this, where pi, I is the state over a number of possible states, and pi is the probability of being in the ith state. E is maximized when all the probabilities are equal because you're equally likely to be in any state, and it's 0 if one of the pi is 1, because there you have absolutely certainty, and all the rest are 0. So in this particular one, we partition the space in front of the participant by a sphere, and the sphere was tessellated into these triangles, and we could count the number of rays from the viewpoint to each triangle as this environment was forming around them, and then obtain the probability of entering any particular triangle, and then use the formula to compute the entropy. So what happened was very interesting. This is the time. This is scan path entropy. So what happens for those who in the stress induction situation, the entropy increases, these triangles are forming, they don't know where they are, and suddenly the entropy drops. When does it drop? Exactly at the moment when they realize they're on a high pillar and their skin conductance shoots up. There's always a short delay in skin conductance compared with the stimulus. So here the scan path entropy increases and then it decreases and then it more or less just oscillates around this. So that's those in the condition where they're standing on top of the pillar. And for those who are at ground level, of course, the entropy is the same. It goes up. Once they realize where they are, it comes down, and then nothing much happens after that. But the skin conductance basically doesn't change. It's just like a horizontal curve. So here we see at the moment that they realized where they were, they get this moment of shock, and that's exactly the moment when they realize where they are. So the drop in entropy is correlated with realizing I am here, I am wherever they happen to be. And also you can see this another way. This is the skin conductance, and this is the scan path entropy, and you can see this negative correlation between the number of skin conductance responses and the scan path entropy. These are the people in the experimental group, and these are the people in the control group. So I'll come back to entropy soon. We introduced also a psychophysics approach analogous to color measurement theory. So in color measurement theory, the sensation of red is a subjective experience, but we can't know if different people actually have the same sensations. But they do agree about what's red, even if their feeling are completely different from each other. Yet there's a well-founded quantitative model for color perception, and it's this idea that participants are shown a target color from here. They have 3 projector guns, and they can manipulate those guns until the color that they're producing matches the one of the target. So after many people do this many times over many colors, you get how much red, how much green, and how much blue there is that is describing any particular color. So the average over many people determines the red, green, and blue values for the target color. So we use something similar. Any time t, the environment's in a configuration. So these are factors that determine how the virtual environment appears. It could be like resolution, illumination model, and so on. Some particular factor. The participant starts in a particular configuration. At various times, they're offered the possibility to choose any one of the K factors and make a change to improve their, whatever it is we're measuring, their level of presence or plausibility or whatever. Finally, we have a large collection of transitions from one of these configurations to another, and then we learn the order of the transitions. And from that, we can get a Markov probability matrix. This is the probability that if you're in configuration I, you would make the change to configuration J. And from that, we can compute various probabilities of interest, like given that you're in configuration C, what's the probability you stop and say, okay, I've matched the level of plausibility or place illusion or whatever it is you're measuring. This is not going to get any better, in other words. So this is our own past use over many papers. Our first paper on this was 2010. Our recent one, this is wrong, it was 2025. This was before it was published. And this is used by others, so it's a method which is gradually catching on. And here's an example. We had an environment where there were 4 different factors where participants watched the string quartet, and they could manipulate gaze, whether the string quartet were looking at them sometimes or not, the oral spatialization, mono, stereo, or spatialize, the oralization, dry, large, or real, and the environment, no environment, or they hear noises, no sounds from the outside, or they hear sounds from the outside. So this looked like this. Again, I'll wind it forward. It doesn't matter. It's very old, this, but I'll just show it here. So there's the string. So every so often, they make a change to one of those 4 factors. The detail here doesn't matter. I just skip that. So there were 20 participants, etc. It doesn't really matter. They choose these transitions, and they had training, and skip forward, and we computed the probability that any time t they were in configuration I. What's the probability that the next change they're in configuration j? Actually, I'm going to skip this because the details of this don't matter. I just want to show you the kind of things that you can get from it. So here's the probabilities that a particular final configuration includes the gaze factor, that sometimes the avatars playing the instruments would look at you. So there's two different levels of gaze: no gaze, and they do gaze at you. And if they don't gaze at you, the probability you stop at that's in your final configuration is less than 10%. And if they do look at you, it's more than 90%. And so on for all the other factors. It doesn't matter. What's important is that nowhere here have we used any questionnaire or asked anybody about their feeling of being there. They've just making these choices, they're carrying out actions, and we get these responses. And I'll skip this as well. Now, refinements of this method, which we call multimodal matching, participants simply chose transitions not for presence, but according to their preferences. You could use this method for anything, any subjective thing that you're trying to measure. And this one, more important, is that instead of you choosing what to change, there's a reinforcement learning agent that offers choices to you. In other words, it offers you, do you want to change it from low resolution to high resolution? You agree or you don't agree. And the reinforcement learning agent learns the configuration that you prefer. And this was recently published last year in this particular paper at the end. So questionnaires are useful. We can't do much with them because we can't combine scores mathematically. They're ordinal. Just as color science relies on agreement of what's red without needing to know what red really means for an individual, this method only relies on the fact of participant choices. A classic experimental design with k factors needs 2 to the power of k conditions. Here we don't need that at all. Participants kind of find a path through the different experimental conditions. So I'm running out of time. I'm going to skip a lot of things now. Just going to say, I started off by saying that place illusion depends on natural sensory motor contingencies. Well, it's difficult to actually test that because if you play around with sensory motor contingencies, people get sick. But we did actually find a way to do this using the method I've just described, where people were able to change various factors like the resolution, the sound, and so on, the illumination. But one of the factors they could change was simply the color. And the color is not a sensory motor contingency. We are interested in would they end up changing the color with more or less equal probability, or would that have a lower probability of being changed compared with the actual factors that were sensory motor contingencies? And that's indeed what we found. The probability of changing the color was like 50-50. The probability of changing a real sensory motor contingency was much higher. So that was in this environment. Participants could change various factors. It's the same string quartet. This is changing color. This is the non-sensory motor contingency. And here the string quartet starts. This is changing the resolution. So here they change the resolution. I don't know if you see that. That's a sensory motor contingency. Let's look for one more. This is the color again. This is being thrown up by the reinforcement learning agent, so we have no control over the order. and there were these 5 factors. These are the things they could change. The first 4 of them are sensory motor contingencies, but color is not. And as I said, the expectation is that participants would change the color with roughly equal chance, but be much more likely to change the first 4 factors of vision, parallax, audio, and resolution. And that's exactly what happened. So we don't have time to go into this. And a very interesting result is this is a questionnaire measure of presence. And this is the eye scan entropy, the entropy of the eye movements. And these 3 don't count because things went wrong with the trial. And what we find is this nice negative correlation, just as we did in the first experiment I showed you before in 2009, between place illusion and the eye scan path entropy. This negative correlation. As they get into higher levels of presence, the entropy of their eye movements decreases. So now I'm just going to say this. Often you do an experiment, you do the kinds of things I just said, measure various factors and so on, but you never get behind the scenes. So what we've started to do in the last few years is always ask people to write down comments that we then use sentiment analysis to analyze. And what happens when you do that is you find out things you would never have discovered by physiological measures, by this multimodal matching, or by questionnaires or anything like that. It gets behind the scenes to find out what's going on, and thereby you can really understand what's happened in your environment and improve it. So I'm going to skip all of that. As I said before we started, we identified many problems in this particular application I have no time to describe. We never would have found those if we'd not done the sentiment analysis. So presence and pi, actually, let's go back one. So using questionnaires, we would never have discovered the various issues. We might have got high scores on presence on the questionnaire, but we'd never have found out the things that were wrong. Presence can be high, but sentiment low. It's good for generating information to improve an application. So resume, we considered key illusions, place illusion, plausibility, body ownership, co-presence, didn't say much about that, the result in VR working. We considered applications, fear of heights, police racism in the US, and we didn't consider the concert, we didn't have time. And then we looked at measurement and considered the entropy of eye scan path, multimodal matching, and getting behind the scenes with sentiment analysis. These are various people in my lab involved in various aspects of this. And the last experiment I described, the one with the multimodal matching and the entropy, this was done as our first experiment in the Presence project. So I run kind of late. I'm willing to stay after the end of 1 hour. I'll stop sharing. If people have any questions, then please put those into the chat.
Thank you, Mel. Thank you very much for your presentation. I just want to remind all the participants while they write questions, if any, that we will have next week the second webinar of the Presence project. And the speaker will be Frank Steinecke. He will be talking about the technologies that we are developing about intelligent smart virtual avatars. I have a question, if I may.
Yeah.
You know that we are working on volumetric capture real time, right? And like 5-6 years ago, we observed, we never did any formal experiment, but we observed that when the users were captured in volumetric video, they were looking at their hands, right? First thing you do is to look at your hands. And then I asked them to touch themselves. Look at you, like look at your belly and touch your belly. And that was like a click. They made like a click. So my question is, for embodiment, that is something that we are not deeply exploring in Presence, or still not exploring in Presence, embodiment with alloported users. being yourself is not the most, let's say, is the most, how to say, embodied condition. Embodied condition, I mean, you have been with your body all the time. I wear this sweater today, so when I get into VR, the marks for embodiment will hit higher if I am myself with my own body and my own clothes and everything, or I'm assuming too much.
Okay, so there is some disagreement about this. So in our experience, you do not have to look like you really look. So our very first experiment on embodiment is we embodied men in the body of a young female, and there was no issue about the body ownership. Why? Because you got this sensory motor, you've got the multi-sensory integration. You move and the body moves with you, and you look down and you see a body in all of your life. Whenever you've looked down, you've seen a body as your body. So people had a high level of body ownership. Obviously, if the body does look like you as well, and you run an experiment where sometimes the body looks like you and sometimes it doesn't in different conditions, then obviously you're going to say the one that looks like you is your body because it looks like you. But let's say scientifically, it doesn't have to look like you. Now, talking about touching the body, years ago, we actually did an experiment exactly like that, where we put people in the virtual reality, they looked down, and either they had a belly that was much bigger than theirs, or it was normal size. And we arranged it so when they tapped the big belly, they felt it as well. I won't go into all the details of how this was done. And then that altered their own self-perception when they came out of virtual reality, and they had the feeling that their real belly was bigger than it really was. So it's very, very powerful. This self-touch is really powerful. If you can organize it that you touch yourself and you feel it, this can actually alter your, temporarily, of course, at least I hope so, your self-perception of your body. So it's a good point to make.
It came naturally, I mean, by
Yeah.
like touch yourself, and then it was like a click. They were like, wow. Well, of course,
Yeah.
if you do
Yeah.
like this, you're going to feel yourself. But when they did this in VR, it was like something happened in their brain. Ladies, I think we have a call.
Yeah, people are putting questions in the Q&A, not in the chat. So the first question is, we have this, are sensory differences, sensory impairments factored into the experiment? And if so, how might it change how we measure perception? I'm not sure I completely understand. So you mean if somebody has poor vision or something like that, or some other impairments, how might this change? Well, I'm not sure how it would change. Provided it's a visual experiment and they can see at all, in the virtual reality, they would see like they would in reality. So, if they have, like, say, partial vision in reality, they have partial vision in the virtual reality. So that shouldn't really change. The second, I don't know. We've never really studied that, but that's my initial reaction. Somebody else says, a question, from my understanding, all presence measured are made at a certain point in the experiment, often at the very end, but wouldn't it be interesting to acknowledge the evolution of pi and psi throughout the experience? So first of all, the one that we use, the multimodal matching, where you can make changes during the course of the experiment, this is happening during the actual interaction, during the actual experience. So it's not something you get at the end. You're measuring it all the way through. And yes, there have been some studies over the years which have used questionnaires where, like, you have a slider or something and you show how presence changes during the course of the questionnaire, during the course of the experience. Again, it's not something we've done ourselves, but it's certainly been done before. But I want to emphasize that the multimodal matching doesn't measure at the end, it measures during the actual experience. Are there any other questions?
No more questions. Okay, then I think this is everything for today. It's 18
Yeah.
sharp. So
Thanks for Sergi, and thanks Maria for organizing. No, there is another one. Oh no, it's not. No, it's one we already dealt with. Thanks Maria. Thanks Sergi.
thank you everyone, and see you next
Thank
week.
you. Bye
Take
bye.
care. Bye bye.
Thank you very much, Mel and Sergi. Bye.
Thank you,
Bye.
Mike.